Welcome to Module 08 of the Data Center Fire Protection Masterclass. This module focuses on the fire-water systems that support reliable response, from approved water demand and storage through delivery, testing, maintenance, and restoration. The central theme is a complete, dependable fire-water pathway. We'll look at the major equipment and interfaces that make that pathway work together. That includes the electric split-case fire pump and its primary electric driver, the diesel split-case fire pump as an independent standby driver, and the vertical inline multistage jockey-pump for constant speed pressure maintenance. We'll also cover the underground fire water tank and vertical-turbine pumps, along with hydrants, the fire department connection, and the brigade interface. The technical framework for this workbook includes NFPA 20, 22, 24, 14, and 25. These references support the design and lifecycle expectations addressed here. As we move through the module, the practical sequence is simple. Design the system correctly, test it rigorously, maintain its readiness, and restore it properly after use or impairment. The goal is confidence that the system will perform when the data center needs it most. This module focuses on architecting an unbroken fire-water chain for data center fire protection systems. The central idea is continuity. Every part of the system, from the water source through active discharge, must work together as an integrated path. The system status is active, with the design basis grounded in NFPA 20, NFPA 22, and NFPA 24. The color system provides a visual language for following that path. Blue identifies suction and source water. Red shows the active main and discharge route. Green marks test returns, helping distinguish testing functions from the primary flow path. Orange represents pressure sensing, described here as the nervous system, because it communicates pressure conditions throughout the arrangement. Purple identifies relief and waste. As we move through Module 08, these colors will make the technical visuals easier to interpret and help us trace how water is supplied, controlled, discharged, tested, monitored, and safely relieved. The goal is not to view isolated components, but to understand the complete chain as one coordinated system. This module provides a clear roadmap for the data center fire protection system. Its purpose is to teach the complete fire-water path, from establishing the demand basis through brigade operation, and to show how each design decision can be calculated, checked, and demonstrated in the field. We will cover tank volume, suction conditions, pump flow and head, system zoning, drivers, and field test results. The primary audience includes owners and facility management teams, fire protection, plumbing, and MEP engineers, as well as commissioning agents, specialist contractors, pump vendors, BMS and FACP integrators, authorities having jurisdiction, and insurer reviewers. That range reflects the need for coordinated decisions across design, installation, operation, and acceptance. By the end, participants should be able to read the fire pump room schematic, follow the full fire-water calculation chain, coordinate pressure settings and test methods, and create audit-ready design and lifecycle evidence. The key output is practical, editable worked calculations, including demand, storage, suction, pumps and drivers, hydrants, standpipes, FDC, pressure control, and acceptance. A 10-story example connects each retained formula to a real decision, its value source, and field proof. This module is organized into 6 sections, moving from system strategy through design, testing, operations, and calculation. The overall goal is to connect the data center's fire protection architecture with the evidence needed to prove that it will perform when required. Section A establishes the standards, design basis, and broader data center strategy. Section B then focuses on the fire-water source, storage arrangements, and pump room architecture. From there, Section C follows the distribution network, including hydrants, the fire department connection, and the interface with the responding brigade. Section D addresses fire pump testing, pressure settings, and performance verification. Section E shifts to the lifecycle: operations, inspection, testing, maintenance, impairment management, and evidence governance. Finally, Section F is a focused calculation workbook. It covers only water-based calculations that support decisions about demand, storage, pumps, distribution, sizing, pressure control, and acceptance. The training method is intentionally practical. Sections A through E build the architecture and controls, while Section F applies calculations where they directly support a design or acceptance decision. This slide presents the firewater architecture for the data center fire protection system. The design begins with a two-cell firewater tank, with a valved equalizing line between cell 1 and cell 2, providing a shared source for the system. Blue lines represent suction, feeding the electric fire pump, diesel fire pump, and jockey pump. Each pump includes isolation and check functions, with controls shown separately, and all discharge flows into the common discharge header. From that header, protection is distributed to the sprinkler or pre-action system, standpipes and hose connections, the yard hydrant loop, and the fire department connection, or FDC. The green path is the metered performance test return, routed back to the tank and located remotely from the intakes. Relief and waste paths are shown in purple, including the diesel pump's main relief logic and the enclosed waste cone with a visible return. Finally, orange pressure sensing lines connect the pumps to their controls. The key design principle is that relief, sensing, testing, and return paths remain independent, visible, and appropriately protected from unintended isolation. This slide establishes the data basis for the training model. NFPA 20-2025 is the benchmark used for this module. The system is organized around two maintainable tank compartments, independently connected electric, diesel, and jockey pumps, dedicated sensing lines, visible relief routing, and one common performance test loop. The source arrangement includes equalizing refill, overflow, drain, access, and level provisions with dedicated intake paths for each pump. The pump set uses an electric horizontal split case main pump, a diesel standby pump, and a constant speed vertical inline multistage jockey pump for the positive suction option described here. Each pump has its own controller and sensing line, tapped at the specified discharge location, rather than using a common sensing header. Relief and testing are deliberately separated. The electric pump's churn relief drains to the pump room sump or an approved drain, while diesel and jockey pump relief are conditional. The shared flow meter return goes back to the tank away from pump intakes. Pressure examples are training values only. Final settings depend on calculations, equipment data, pressure ratings, and AHJ approval. This section establishes the standards, authority hierarchy, and reference basis for the data center fire protection system. The primary water system references are NFPA 20 for stationary fire pumps and controllers, NFPA 22 for private fire protection water tanks, NFPA 24 for private fire service mains, and NFPA 25 for inspection, testing, and maintenance of water-based systems. These standards connect with other requirements. NFPA 13 supports sprinkler and pre-action water demand calculations. NFPA 14 addresses standpipes and hose systems where required. NFPA 72 governs water flow, tamper, pump, and supervisory signals, and NFPA 291 provides context for hydrant flow testing where adopted. Local SNI requirements, the applicable fire code, and DAMCR or AHJ acceptance requirements also apply. FM Global or insurer guidance, manufacturer instructions, and owner operating policies may add further controls. The key governance rule is the legally adopted code and AHJ approval control acceptance. Other references strengthen reliability and lifecycle evidence, but settings, test procedures, valve lineups, and bypass status must not change without formal management of change. This slide establishes the governance paradigm for the fire protection system, and the central idea is compliance is not a matter of personal engineering preference. The system is dormant industrial architecture, meaning it may sit unused for long periods, but it must perform immediately and reliably when demanded. Its design and acceptance are governed by legally adopted National Fire Protection Association standards, specifically NFPA 20, NFPA 22, and NFPA 24. The flow begins at the source, moves through the campus loop and pump station, and then reaches the sprinkler and hydrant interfaces. Each stage is part of one connected defense, not an independent feature. That connection also creates the system's criticality. A seized hydrant, a dead battery, or a closed valve can interrupt a single link and sever the protection provided by the entire multi-million-dollar network. So final acceptance does not rest with the designer or operator. It is controlled exclusively by the authority having jurisdiction, or AHJ, which verifies that the installed system meets the adopted code requirements. This module begins with the design basis for a data center fire protection system. Before we detail the pump room, we need to establish the governing standards hierarchy, determine the required fire water demand, define the water source strategy, agree on the pump philosophy, and understand the owner's risk requirements. The key principle is to design, test, maintain, and restore the system as one continuous life cycle, not as separate activities. In this section, I'll focus on 4 outcomes. First, we'll define what makes the water source acceptable and what readiness requirements apply to the pumps. Second, we'll translate standards into testable evidence, so compliance can be demonstrated rather than assumed. Third, we'll align the expectations of the authority having jurisdiction, the insurer, the equipment manufacturer, and the owner. Finally, we'll connect those decisions to the physical arrangement, including the fire water distribution main and the common fire pump discharge header. Establishing this foundation early helps prevent later conflicts between design intent, acceptance testing, operations, and restoration after an event. This section establishes the fire water design basis for data center campuses. The starting point is to identify every demand source that could operate during an event, including sprinkler or pre-action remote area demand, hose allowance, standpipe or hose valve demand, external hydrants, brigade support, and any special local water requirements. From there, the critical design questions are practical and consequential. Which combination of loads governs the fire pump and tank size? What duration must the system support? What residual pressure is needed at the most remote zone? And can a tank cell or distribution branch be taken out of service without creating an unacceptable impairment? The design also needs evidence, not just equipment labels. That evidence includes the hydraulic calculation, water supply and pump curves, a statement of usable tank volume, flow test results, the pump acceptance report, and documented AHJ or insurer comments with closure. The complete chain from the water source to the most remote protected area and the brigade interface must be proven. A stable pump curve, proper suction conditions, and clear distribution zoning matter, just as much as the pump's rated capacity. This slide presents option 1, an above-ground, 2-cell firewater tank serving 3 dedicated pump branches. The key design principle is positive suction. The minimum operating water level remains above every pump centerline, so the pumps have flooded suctions and require neither priming nor foot valves. The electric and diesel fire pumps use horizontal split case configurations, while the jockey pump is vertical inline and maintains system pressure. Each pump has its own tank outlet, anti-vortex intake, and supervised isolation. There is no common suction, which helps preserve independence and reliability. All 3 pumps discharge into a common firewater header serving the sprinkler zones, standpipes, yard hydrants, and fire department connection. Return paths remain separated. The diesel minimum residual valve and engine water cooling return go back to the tank through a visible, independent path without a shutoff valve. Metered test water also returns separately away from pump intakes to reduce vortex potential. The design proof therefore focuses on water level, flooded suction geometry, supervised valves, independent returns, and full flow testing. This slide presents option 2. An underground tank with vertical turbine mains and a jockey pump. The arrangement uses a 2-compartment wet pit, with an electric fire pump and a diesel fire pump connected to a common fire pump discharge header. A constant speed, vertical multistage jockey pump maintains system pressure during small losses, while the main pumps provide the required fire flow capacity. The vertical turbine basis is important because this configuration is intended for a water source below the pump elevation. Before selecting it, I need to confirm several physical and structural conditions. Adequate bowl submergence, proper column alignment, sufficient wet pit geometry, structural loading, removal height, and clear access to the pump deck. The supporting equipment includes the electric and diesel controllers, diesel engine, right-angle gear, batteries, fuel tank, pressure gauges, automatic air release, check and OS&Y gate valves, and a concentric discharge increaser. Testing and pressure relief are handled through the flow meter, main relief valve, and open discharge overflow cone. Finally, the diesel package includes the flexible exhaust connection and muffler, while the relief return remains independent. Module 08, Section B, focuses on fire water sources and pump room architecture. The central idea is to stop viewing each component as an isolated piece of equipment. Instead, I want us to understand the source, storage tank, suction piping, electric pump, diesel pump, jockey pump, test line, and discharge header as one operating platform. The goal is an integrated, maintainable fire protection system. That means we will examine how the physical arrangement of the pump room affects hydraulic behavior, including how water moves through the system and how the equipment works together under different operating conditions. We will also pay attention to maintainability from the beginning, because access, testing, servicing, and restoration are not secondary concerns. They are part of the design. By the end of this section, I should be able to read the pump room components as a functional chain, connect layout decisions to system performance, and identify constraints before they become operational problems. The working cycle is simple: design the system, test it, maintain it, and restore it when needed. This slide presents the end-to-end architecture as one connected fire protection chain, moving from the water source to the systems inside the data center. The key idea is continuity. Every layer has a defined role, and each handoff must remain clear and reliable. The first layer is the source and pump station, including the tank, pumps, controllers, and test or relief functions. From there, water enters the private fire main, or campus loop. The looped arrangement includes sectional valves, hydrants, and fire department connections, allowing the distribution network to serve multiple points while supporting isolation and access. The third layer is the set of protected system interfaces within the building. These include sprinkler and pre-action systems, standpipe and hose connections, and hydrant or riser interfaces. The external hydrant and FDC, or Siamese connection, provide visible brigade access points. So the readable sequence is straightforward: fire water source, pump set, looped fire service main, hydrants and FDCs, then the sprinkler, pre-action, and standpipe systems that protect the building. This slide compares two extraction architectures, and the key distinction is how each arrangement creates suction at the pump. Option 1 is above-ground flooded suction. The tank and pump rooms sit at the same level, using horizontal split-case EFP and DFP pumps, along with a vertical inline jockey pump. Because the minimum operating water level remains above the pump centerline, gravity provides positive flooded suction. In practical terms, water is physically pressing toward the intake, which supports a straightforward and stable suction condition. Option 2 is an underground wet pit arrangement. Here, the wet pit is divided into two below-grade compartments, with vertical turbine main pumps and a vertical multistage jockey pump. This relies on negative elevation draft, so performance depends on mechanical draft, strict bowl submergence, and precise vertical alignment. The design note is critical. The architecture must be frozen before any duty is calculated. Maximum pressure is an architectural boundary, not simply a number assigned to one pump. That decision governs the entire hydraulic design. This slide presents the same level, positive suction option 1 layout for the fire pump room. The two-cell fire water tank and pump room share the same elevation, so the minimum operating water level remains above every pump centerline. That is the basis for positive static head, and it must be proven under the usable volume condition. The suction arrangement is deliberately independent. Each pump has its own dedicated, flooded branch, anti-vortex intake, and supervised isolation valve, with no common suction header. The electric and diesel pumps use horizontal split-case configurations, while the jockey pump is a constant speed, vertical inline multistage unit used only for pressure maintenance. Downstream, all three pumps feed a common discharge serving the sprinkler zones, standpipe hose valves, yard hydrant loop, and FDC or Siamese connection. Returns are kept separate. The diesel minimum flow and excess water return goes visibly back to the tank without a shutoff valve, while the metered test return is remote from every intake. Final approval depends on documenting the water level, flooded suction geometry, supervised valves, independent returns, and full flow testing. This section maps the pump set components and clarifies who owns each part of the system. The key requirement is that every physical component can be traced to its controller, its test method, its normal operating position, and evidence that it was restored afterward. The hydraulic scope includes 3 direct tank suction branches with anti-vortex intakes, suction isolation valves, eccentric reducers where applicable, discharge check and indicating isolation valves, the common discharge header, flow meter and relief returns, and the distribution branches. The mechanical scope covers the electric and diesel horizontal split case pumps, the vertical inline multistage jockey pump, and the diesel engine systems, bases, couplings, supports, drains, and maintenance clearances. Control ownership includes a dedicated controller and sensing line for each pump, pressure sensing devices, test connections, alarms, and event logs. Monitoring can reach the fire alarm panel, building management system, or security operations center, but without undocumented control authority. Acceptance evidence must match the component. That includes tank level and suction inspections, pump controller and curve records, diesel relief and engine tests, jockey pump cycling and leak reviews, and documented valve lineup, meter calibration, visible return flow, and restoration for common testing. This matrix distinguishes the 3 pump archetypes by role, driver, relief logic, and discharge routing. The electric fire pump, or EFP, is the primary heavy responder and auto-starts when fire flow demand requires it. It uses a constant speed grid electric motor, with only a casing relief valve, or CRV. Its discharge drains to the pump room sump, shown in purple, and does not use a main relief valve. The diesel fire pump, or DFP, provides total blackout standby. It is driven independently by a diesel engine with its own battery and fuel systems. Because of that role and configuration, a main relief valve is mandatory. Its relief discharge routes to an enclosed waste cone, then returns to the tank. Finally, the jockey pump is not a fire flow source. Its job is routine pressure maintenance, using a vertical inline multistage electric pump. It has a conditional jockey pressure relief valve, or JPRV, and its discharge can drain either to the sump or back to the tank. Together, these rules keep each pump aligned with its intended operating condition. They also make clear that relief protection and routing are not interchangeable across the 3 systems. This slide shows the hydraulic and control arrangement for an electric horizontal split case fire pump, or EFP, serving a 2-cell tank. The tank cells are connected by a valved equalizing line, while the pump suction and discharge sides include supervised isolation valves, pressure indicators, and a discharge check valve. The key protection device is the casing relief valve, or CRV. Its purpose is to prevent the pump from overheating during churn when the discharge is closed. It is located on the pump casing, upstream of the discharge check valve, and must discharge independently to an approved open drain or pump room sump. The CRV is sized according to the pump's rated flow, from 3/4 of an inch through 2,500 gallons per minute, and 1 inch for 3,000 to 5,000 gallons per minute. The dedicated pressure sensing line is tapped between the discharge check valve and the indicating isolation valve and connects to the electric pump controller. During acceptance, I would verify the suction valve is open and supervised. The controller is an automatic. All components can handle maximum total shutoff head. The pump curve is approved, and the CRV drain capacity is adequate. This section establishes a critical sequencing rule. Pump architecture is frozen before any duty is calculated. The design logic moves in a controlled order from demand scenarios to the availability target, then the suction boundary, pump arrangement, and finally the calculation route. First, demand ownership is defined through NFPA 13 and NFPA 14 requirements, together with AHJ fire flow expectations and the approved demand matrix. We should not add unrelated maximums. Next, the resilience target considers impairment and common cause risks, while the owner decides whether systems are combined or separated. The hydraulic boundary is then fixed around the tank, suction conditions, zones, and highest outlet. That creates one frozen geometry for every subsequent calculation, avoiding changes in the basis as the design progresses. The formal handoff goes to section F4, where flow, total dynamic head, NPSH, drivers, pressure-reducing valves, and testing are controlled. In short, sections B and C define the architecture only. Pump selections and all equations remain governed by the project design basis, NFPA 13 and 14 demand, NFPA 20 arrangement, and AHJ or Damker concurrency approval. This section establishes a critical design principle. Maximum pressure is an architecture boundary, not a single pump number. The governing condition is created by several factors working together, including the highest outlet, pressure zones, certified churn pressure, maximum suction pressure, and potential surge. The design checks begin with the most remote service points, particularly roof standpipe and sprinkler routes. We identify governing nodes, then verify the detailed hydraulics in sections F3 and F4. At the low floor, churn pressure combined with maximum suction determines the required component class for headers, valves, and fittings. The control strategy must also work across both high and low flow conditions. That may mean a direct high zone with listed pressure-reducing valves, but it cannot be based on static pressure alone. The evidence must include the pump curve, zone tests, surge review, and a complete acceptance package that supports procurement and commissioning. The architecture decision is to freeze pressure zone boundaries and component ratings before procurement. Section F will establish the exact values, using NFPA 14, NFPA 20, listed PRV data, and certified component information as the governing references. This slide defines the system boundaries for a separated fire protection architecture. The central idea is that a sprinkler impairment should not automatically disable hydrant and standpipe service, and the reverse should also be true. Each duty has its own complete train. For the sprinkler system, that means an independent electric and diesel pump pair, a dedicated header and riser arrangement, and a dedicated test meter with its own return. The hydrant and standpipe train follows the same pattern, but remains hydraulically separate. The tank suction is the only shared interface identified here, and even that connection is subject to the approved tank cell plan. This separation also creates distinct impairment boundaries. Testing, valve supervision, and records need to demonstrate which train is affected, while the owner and authority having jurisdiction review the impairment scenarios. The recommended architecture is to calculate the two duties separately, evaluating a combined set only as a conditional alternate. Final design evidence must address NFPA 20 requirements, project reliability criteria, and the required owner or AHJ approvals. This slide establishes the design control logic for the handoff from Section B to Section F. The central point is that one architecture decision controls every downstream calculation. Once the architecture is defined, the demand matrix is approved, the reliability basis is separated, and the hydraulic datum is frozen, the later calculations should not quietly redefine the system. The preferred worked example uses separated sprinkler and hydrant or standpipe trains, supplied from a two-cell tank. That arrangement becomes the basis for the Section F3 standpipe and yard calculations, followed by Section F4, which addresses the tank and pumps. The output is a single final equipment schedule, and that schedule is audited before release. A combined 2,000 gallon per minute arrangement is still identified as an alternate, but it requires review by the authority having jurisdiction and the owner. So, it is not the controlling basis for this workflow. The governing references are the project design basis, NFPA 13 and NFPA 14 demand requirements, NFPA 20 pump arrangements, the owner's resilience criteria, and final AHJ or Damker approval. Together, these controls keep the calculations traceable and prevent architecture changes from propagating unnoticed. This slide shows the diesel fire pump arrangement and the conditions governing its relief and return piping. At the center is the diesel fire pump package, with suction from the two-cell firewater tank through the valved equalizing line, and discharge through the isolation valve and check valve to the common header. Pressure indication is provided on the suction and discharge sides, with dedicated sensing for the diesel pump controller. The main relief valve, or MRV, is conditional. It is required when 1.21 times the pump's net rated churn pressure, plus the maximum static suction pressure adjusted for elevation, exceeds the rating of a system component. When an MRV is required, Its discharge is arranged between the pump and discharge check valve. The return must be visible or detectable through the EWC, independent, directed back to the firewater tank, remote from tank intakes, and installed without a shutoff valve. The final point is diesel readiness. Before and after testing, verify fuel, batteries, charger, cooling, exhaust, controller auto status, leakage, and complete restoration. This slide focuses on the diesel fire pump's overspeed failsafe, centered on the main relief valve, or MRV. Because a diesel engine can overspeed, it may generate a dangerous level of pressure very quickly. The MRV provides a high-capacity path for that overpressure, directing relief water from the discharge header back to the supply tank. The enclosed waste cone, together with its sight glass, gives operators a direct visual check that water is actually flowing through the relief system. That visual confirmation is important because it verifies the valve and discharge path are functioning when protection is needed. The most critical installation rule is no shutoff valves permitted. If a valve in this path is accidentally closed, pressure can become trapped almost immediately. The resulting pressure can blow engine seals and disable the very failsafe intended to protect the pump. So, when inspecting this system, I would confirm the MRV's connection to the discharge header, the return path to the supply tank, visible flow at the sight glass, and an uninterrupted, non-isolatable relief path. This slide presents two installation options for a jockey pump, using a vertical inline, multi-stage, constant speed pump with positive suction. The key requirement is a reliable, flooded, or otherwise positive suction arrangement, with a dedicated discharge check valve, isolation valve, and independent sensing line. Option 1 uses an above-ground 2-cell tank. The cells are connected by a valved equalizing line, and the jockey pump control system monitors pressure through its dedicated sensing line. Option 2 uses the water tank mains or another positive suction source, with the pump located at the grade or pump deck and discharging to the common header. The pressure hierarchy shown for a 70-meter data center building is also important. The jockey pump cuts out at 16.5 bar, cuts in at 15.5, the electric fire pump cuts in at 14.5, and the diesel fire pump at 13.5. Frequent jockey pump cycling is a warning to investigate leakage, check valves, or open drains. Finally, the jockey pump relief valve is conditional. It is required only when shutoff pressure could exceed the system rating, or when a turbine vane pump is used, and it must be sized to prevent overpressure. This section addresses dedicated controller pressure sensing lines. The key principle is simple. Each automatic pump senses pressure through its own independent line. The electric fire pump has one sensing line from its discharge branch to the electric fire pump controller. The diesel fire pump has a separate line to its own controller, and the jockey pump has a third dedicated line to the jockey pump controller. Each sensing point is taken from the pump's discharge branch, between the check valve and the indicating isolation valve. That arrangement avoids a common sensing header and keeps each controller responsive to the pressure conditions of its associated pump. Material selection is also important. NFPA 20, Section 4.32, requires corrosion-resistant sensing line materials such as brass, rigid type K, L, or M copper tube, or Series 300 stainless steel. Black or galvanized steel can corrode and obstruct the small orifices, delaying or preventing an accurate pressure drop signal. Finally, any sensing line isolation is treated as an impairment, and the function must be retested before the system is returned to service. This slide illustrates a coordinated pressure ladder for constant speed fire pump logic. The purpose is to make each pump respond to a different level of pressure loss, rather than having multiple pumps start at once. The sequence begins with the jockey pump. At 16.5 bar, it is shown at cutout, and when pressure falls to 15.5 bar, it starts to restore pressure caused by minor leakage. If pressure continues to fall, the electric fire pump starts at 14.5 bar. With sustained demand, or under the applicable standby logic, the diesel fire pump starts at 13.5 bar. This staged response helps distinguish small losses from a genuine firewater demand. Main pumps are generally stopped manually after the initiating cause has cleared, unless the adopted code, listed controller, and approved sequence specifically permit otherwise. These are training values, not final design settings. Final values must follow the hydraulic calculation, pump curves, pressure ratings, controller listing, manufacturer data, and authority acceptance. Frequent jockey starts, pressure oscillation, or overlapping pump operation should prompt investigation of leakage, failed check valves, open drains, or poor coordination. This matrix defines how different relief and return functions are triggered, where they discharge, and which rules control their installation. The key principle is that each function has a dedicated routing path and must remain properly separated. For casing relief, the trigger is zero-flow boiling friction or closed discharge, also called churn. The flow routes to the pump room sump or an open drain, and this relief valve is required on constant speed electric pumps. The main relief valve addresses diesel engine overspeed, overpressure, or pressure that exceeds a component's rating. Its return must go independently back to the tank through the waste cone. Importantly, no shutoff valves are permitted in that path. The metered test return serves a different purpose. It manages air vortex generation during manual performance testing, and the return must be routed independently, remote from the intakes. It also must not be mixed with relief lines. Together, these rules prevent incompatible flows from sharing a route and make sure each relief or testing condition has a controlled destination. This slide presents the three-dimensional campus interface for the fire department connection, or FDC, the Siamese connection, and the tank refill system. The central message is that these functions must remain clearly separated by purpose, color, labeling, and operating responsibility. The FDC and Siamese connection support Brigade pumping into the protected fire service distribution system. They should remain visible, clearly signed, unobstructed, and compatible with local coupling practice. The tank refill or makeup path serves a different purpose. It restores fire water storage and supports source resilience, but it is not a substitute for FDC pumping into the distribution network. The pump room and brigade staging areas should reinforce that distinction in both layout and training. The slide also calls out backflow protection and isolation. Backflow preventers, check valves, and sectional isolation points need to be accessible, labeled, supervised where required, and returned to their normal operating condition after use. The practical training rule is simple. Never use the same label, color, or emergency instruction for FDC, tank refill, and fire pump discharge. AHJ means authority having jurisdiction. This slide shows the no-mix routing logic for system returns. The central idea is that each return path stays isolated, so one flow condition cannot hide or distort another. Returns remain isolated. Path 1, labeled EFB-CRV, is the short route, running directly to the floor sump pit. Path 2, for the DFP, MRV, and EWC, follows a longer, visible line back to the fire water tank, with no shutoff. Path 3 is the metered test route. It passes through a calibrated flow meter before returning to the tank. This separation is important because combined returns could create overlapping failures, mask back pressure, or produce false sensing. The diagram also highlights a specific requirement for high-volume test returns, shown in green. Those returns must terminate well away from the pump intakes inside the tank. The purpose is to prevent vortex creation during annual testing, which could interfere with reliable system operation. So the routing is not simply about where water goes. It is about maintaining clear, independently observable paths and protecting the accuracy and stability of the fire protection system. This section focuses on how the fire pump discharge connects to the broader data center campus. The goal is not only to move water, but to make sure that water reaches the right protection systems and remains usable during an emergency. We'll examine the service split between low zone and high zone areas, including how sprinkler zones, hydrant zones, and standpipe interfaces fit together. We'll also connect the fire department connection, or FDC, to the brigade's pre-plan, so responders can understand where to connect, what systems they are supporting, and how campus access affects their operations. A major theme is coordination. Hydrant locations, FDC access, signage, and access roads all need to support fast, reliable response. The water supply must also be controlled and documented through testing and proof of performance. The operating mindset for this module is simple: design, test, maintain, and restore. These 4 actions help keep the distribution system ready before an incident, functional during one, and dependable afterward. This slide presents the generalized distribution zoning strategy for a data center campus. The central idea is to divide fire protection systems into branches that match the areas they serve and the pressure conditions they require. Every branch must answer 3 questions. What does it protect? What pressure does it need? And how will the team prove it is available without disrupting operations? For sprinklers, the low zone typically serves lower floors and support spaces, with control through pressure-reducing valves, floor valves, water flow devices, and tamper switches. The high zone serves upper floors or roof-level areas, where pressure may require a dedicated valve arrangement or pump discharge branch. Hydrant zones follow the same logic, separating external hydrants and lower standpipes from upper standpipes and high riser networks. The FDC, or Siamese connection, provides supplementary input for the fire brigade. Its readiness depends on the check valve, clear signage, pre-planning, and periodic condition checks. Evidence of availability comes from drain tests, flow tests, hydraulic proof, and hose valve pressure testing. This section presents the fire brigade interface through a 3D campus operational map. The purpose is to connect the site view with editable, numbered callouts, so responding crews can quickly identify the locations that matter during an incident. The key requirement is to keep the fire access infrastructure clear and usable at all times. The first point is the FDC, or Siamese connection, which provides the main brigade pumping connection. Second are the external hydrants, positioned along the fire apparatus route. Third is the staging area, where appliances and crews need a clear deployment space. Fourth is the tanker refill point, providing supplemental water where required. The fifth point is the pump room, with operational access to the pumps and controls. Finally, the route to the protected risers must remain clear and properly signed, so crews can move efficiently from the external approach to the internal fire protection system. Together, these callouts turn the campus map into a practical response tool, not just a visual reference. The fire access, hydrants, FDC, and staging area must remain unobstructed at all times. This slide focuses on the external defenses that allow a fire brigade to support, or in some cases challenge, the facility's internal fire protection system. The first application point is the yard hydrant. These are the primary external defense, with the capacity to deliver flows of up to 1,500 gallons per minute. That capability is only useful if the hydrants remain accessible and operable. A seized cap or a buried valve can immediately interrupt the distribution chain, preventing water from reaching the intended point of use. The second application point is the fire department connection, or FDC. This is the brigade's injection point into the facility. Municipal fire trucks can connect here and pump external water into the facility's ring main, supplementing the internal pumps and extending available support during an incident. The key lesson is that external interfaces can bypass all of the internal pump room engineering. If the hydrants or the FDC fail, the entire protection system may fail, regardless of how sophisticated the equipment inside the facility is. That makes inspection, access, and operability at these connection points essential. This section focuses on the external hydrant system, with attention to placement, loop design, and testing. A hydrant needs to be reachable from the fire apparatus access route and clearly visible in both normal and emergency lighting. Where vehicle impact is possible, protection may be necessary, and spacing must provide the coverage required by the adopted code and the authority having jurisdiction. From a system design perspective, a looped main is preferred where practical because it can improve resilience. Sectional isolation helps limit the area affected by an outage, while post-indicator or supervised valves may be required by the adopted criteria. Flushing and drainage also need to be considered, not treated as afterthoughts. Testing should document hydrant flow and residual pressure, while also checking the cap, threads, and operating nut. Confirm that outlets are not obstructed, hidden, or buried, and update the fire brigade pre-plan. Operational usability is the critical test. A hydrant may be hydraulically correct yet useless during an emergency if a truck blocks it, landscaping hides it, the cap is seized, or responders cannot find it in the pre-plan. This section focuses on the standpipe and internal hose valve interface, which supports manual firefighting inside the building. Its effectiveness depends on having adequate pressure and flow at the hose valve outlets, while also fitting into the overall stair, firefighting lobby, and egress strategy. The design checks are practical but essential. I need to confirm that hose valves are easy to find and access, and that pressure-reducing or regulating devices are provided where conditions require them. Drainage, clear signage, and accurate valve tagging also matter. The standpipe arrangement must be coordinated with the fire lift and smoke control systems, so these elements work together during an emergency. Testing should demonstrate that the system performs as intended. That includes hydrostatic or flow-proof where required, checking valve operation in caps or hose connections, recording pressure at representative outlets, and restoring the system to its normal condition afterward. The broader training message is equally important. Periodic proof and route awareness are critical. Because standpipes may not be used every day, their locations should be included in site emergency drills, along with practice finding and operating the valves. This section focuses on the FDC, or Siamese connection, and how it supports firefighter pumping during an emergency. The first priority is field readiness. The connection must remain visible and unobstructed, with clear signage identifying the served system, pressure limit, and building or zone. Caps, swivels, and threads need to stay serviceable, and access must not be blocked by parked vehicles or landscaping. From a design standpoint, the arrangement should include appropriate check valves and drainage, and the connection must route to the correct riser or header. It also needs to be compatible with brigade hose and coupling practices, while being protected from impact and vandalism. During operation, the fire brigade connects to supplement system pressure. The operator identifies the affected zone and confirms the pump room status. The FDC path must not be isolated during routine maintenance unless the proper impairment procedure is followed. The key rule is that the FDC must be part of the complete emergency plan. Show it on the same pre-plan drawing as hydrants, the pump room, gate access, staging, and the route to internal risers. A connector by itself is not an emergency strategy. This section establishes a simple but important rule for the distribution interfaces. Every interface has one hydraulic owner and one calculation destination. That separation keeps responsibilities clear and prevents the design from treating boundaries as shared or ambiguous. The register identifies 5 interfaces. Class 1 standpipes serve 4 wet risers in protected stairs, with their performance calculated in F3 and accepted through remote and additional riser flow testing. Roof hose valves represent the highest required outlets, so the design must verify flowing residual pressure in the high zone. Yard hydrants support the campus brigade through a looped private main, with testing that includes both normal operation and a single isolation route. The FDC, or Siamese connection, is the fire service augmentation point, verified through apparatus pressure and operation. Finally, floor PRVs define bounded preaction horizontal systems, with valve trip and delivery proof assigned to F1 and F2. Section C defines the interfaces, access, and operating boundaries. Section F3 then performs the hydraulic calculations and field test checks, using NFPA 14 and 24, the NFPA 13 preaction requirements, and applicable SNI, AHJ, and DAMCA requirements. This slide presents the pressure zone architecture used to protect system performance across different elevations. The pump header supplies the system, but the building is divided into high, mid, and low pressure zones so that the upper areas receive the pressure they need without overpressurizing equipment and piping on the lower floors. The zone boundaries are based on engineering conditions, not simply on the number of floors. They must account for the maximum credible pressure, the required flowing residual pressure, and the listings of the installed components. The high zone may connect directly, while the mid-zone requires a review of whether a pressure-reducing valve is necessary. The low zone uses a listed PRV where required. These decisions are then verified through field testing at both high-flow and low-flow conditions, because stable performance must be demonstrated across the operating range. The detailed calculations, including remote residual pressure, churn exposure, and PRV stability, are completed in F3. Section C retains the final architectural boundary. The governing references are NFPA 14, NFPA 20, and the applicable listed PRV performance curves. This slide shows how acceptance evidence closes the loop from design through field verification and controlled handoff. Every interface must connect calculation proof, a witnessed field test, and a controlled record. For the standpipe system, that means confirming the remote and additional risers, then demonstrating simultaneous hose valve flow, with AHJ or commissioning witnesses and an F3 acceptance sheet. Pressure zones require maximum and minimum inlet and outlet calculations, followed by high and low flow testing of the pressure-reducing valves. The private main is checked for both normal and single isolation routing, along with flow, hydrostatic, and flushing tests. For the FDC or Siamese connection, the team verifies apparatus pressure and flow, then performs a brigade connection test. Finally, restoration confirms that valves and controls return to their normal state, supported by a post-test walkdown and signed closeout. The design note is important. Values shown earlier remain governed by the controlled calculation and revision status in F3 and F4. Acceptance follows the applicable NFPA references, approved commissioning procedures, and the planned Damker witness arrangements. This slide presents the common flow meter test loop used to demonstrate controlled pump performance. Water is drawn from the two-cell tank, passes through the pump under test, moves into the common discharge header, and then through the listed FM flow meter and throttling valve. The metered flow returns to the tank or to another approved source. The separate relief return is not part of the flow loop, and it must remain independently routed. The test sequence begins by confirming permits, notifications, and the normal valve lineup. I then select one pump for testing and verify the operating modes of the other pump. The isolation valve is opened, and the throttling valve is adjusted slowly to establish each stable flow point. At every point, I record flow, suction and discharge pressures, net pressure, speed, driver observations, and calibration status. Finally, I close the system gradually, restore the valves, controllers, and monitoring, and return every temporary test condition to normal. Gradual valve movement is essential to limit water hammer, and discharge water must be kept away from pump suction intakes. This slide shows how the validation architecture connects measured flow to physical proof. The foundation is the physical loop, where the system is tested across 3 operating points rather than judged from design intent alone. Node 1 represents zero-flow churn, showing how the pump behaves when circulation is present but delivery is effectively stopped. Node 2 is the normal reference point, at 100% of rated flow. Node 3 pushes the system to an extreme overload condition at 150%. The pump curve links these conditions through 2 key measurements, head or pressure on one axis and flow rate on the other. Together, they show how performance changes as the system is driven harder. The most important idea is that physical installation must be proven under its mechanical limits. The design intent is not visible simply because the equipment is specified correctly. It becomes credible only when the flow meter tracks the system through these operating points, including the extreme condition, and confirms that the installed hardware actually survives the test. This module focuses on turning fire pump testing into a controlled, repeatable field procedure. The goal is not simply to start the pump and observe flow. It is to prove the complete performance picture, including shutoff head, churn pressure, flow performance, pressure settings, controller modes, and evidence that the system was properly restored afterward. The central sequence is: establish normal conditions, select the pump, verify the valve lineup, start and flow the system, record the required data, and restore the system. That sequence creates a consistent path from preparation through closeout, while reducing the risk of missed steps or incomplete documentation. The section outcomes are practical. I want to convert testing into a safe field process, use PI, PO, and flow data consistently, and capture evidence for the pump curve, controller operation, and restoration. The architecture shown here connects the tank, EFP, DFP, JP, FM loop, and system or FDC. Together, these elements provide the context needed to understand where the test begins, how water moves through the system, what measurements matter, and how normal service is confirmed at the end. This section introduces the main pump testing philosophy and the test families used to verify fire pump readiness. The first is the shutoff head test, which checks pressure under a no-flow, closed discharge condition. The measured result is compared with the manufacturer's pump curve and the approved acceptance range, with careful valve operation and continuous pressure monitoring. The churn test also operates the pump without intentional flow, but its focus is broader, confirming automatic start, controller response, pressure behavior, and overall mechanical condition. During the test, we record discharge and suction pressure, along with any unusual vibration or leakage. The performance flow test measures capacity at selected flow points through a test header or flow meter. The key points are churn, rated flow, and 150% of rated flow, with intermediate readings added when a more complete curve is needed. We also record pressure, speed, and power input. Most importantly, every test must follow the approved method, OEM instructions, NFPA and AHJ requirements, permits, discharge planning, and impairment controls. The work is complete only after the pump room and connected systems are safely restored. This slide covers the prerequisites and safety controls that must be confirmed before pre-testing the fire protection system. The goal is to make sure the test is controlled, observable, and reversible, without creating an avoidable risk to the data center. No test should begin until the required notifications and permits are in place. That includes operations, the Security Operations Center, fire alarm control panel monitoring, security, and any affected stakeholders. If the system will be impaired, the approved permit must also define a fire watch or other compensatory measures. Next, I need to verify the valve lineup, including normal and temporary positions, and confirm which pressure-reducing valve branches are open or closed for the test plan. Pump controller modes must be clear as well. Only the required pump should be in auto or test mode, while the others are managed according to the approved plan. Instrumentation must be calibrated, with the pressure observation and pressure indication points identified. Finally, the test water discharge route must be safe, and a restoration checklist must be ready before testing starts. This section explains the principle and acceptance logic behind a shutoff head test. The purpose is to verify the pump's no-flow pressure against the approved pump curve or test sheet, while also identifying potential overpressure, controller problems, or hydraulic restrictions. Because the test can create significant pressure, it must follow an approved procedure with a safe discharge and valve arrangement. The valve sequence is equally important. Downstream pressure-reducing valve branches may need to be isolated, and test line or meter valves are opened according to the selected test stage. The discharge is then closed gradually until the pump reaches a no-flow condition. This must be controlled carefully to avoid water hammer and uncontrolled overpressure. The acceptance record should identify the pump and controller mode, document suction and discharge gauge readings, capture the shutoff head, compare it with the manufacturer's acceptance limit, and provide evidence that the system was restored afterward. As a training example, the test sheet uses a limit of less than 140% of nominal head for both electric and diesel pumps. Final pass or fail decisions must use the actual project pump curve and approved procedure. This section presents an example script for an electric fire pump shutoff head test. The sequence is designed to control the test boundary, protect the system, and create clear evidence at every step. First, the permit is opened and monitoring personnel, including the FACP and SOC, are notified. Next, downstream PRV branches are closed according to the approved method, and the valve positions are recorded. The electric fire pump is placed in the required auto or test mode, while the jockey pump and diesel fire pump are secured as defined by the test plan. The first stage test path is opened, then closed slowly to reach a no-flow condition without water hammer. At that point, the discharge and suction readings are captured, with a gauge photo and completed test sheet. The example shutoff head is 17. 98 bar, compared with an acceptance reference below 22.39 bar. Finally, the valve lineup and pump controls are restored. All systems are confirmed normal, and the permit is closed. The quality check is equally important. Record the measured value, instrument calibration, valve lineup, and restoration confirmation. Any abnormal pressure requires engineering review. This slide provides a practical example script for a diesel fire pump shutoff head test. The sequence begins with readiness, confirming fuel, batteries, charger, cooling, and exhaust conditions before operating the pump. Next, downstream branches are isolated using the approved method. Monitoring is notified and valve positions are recorded. The diesel fire pump is placed in the required automatic or test mode, while the electric and jockey pumps are secured as required. The test path is then operated, and the valve is closed slowly until a no-flow condition is reached. At that point, the presenter records both the suction and discharge pressure readings, along with stable engine speed and pressure. The example lists a shutoff head of 17.94 bar, with an acceptance reference below 22.39 bar, or below 140% of nominal head in the example form. The final step is restoration. Return valves, controller modes, fuel and battery status, and records to their normal condition. Diesel observation must include more than hydraulic readings: fuel status, cooling, exhaust, vibration, leaks, and controller alarms. This example script walks through a jockey pump shutoff, or pressure maintenance test. The purpose is to verify that the system holds pressure correctly and that the jockey pump responds in the intended sequence. First, I confirm the normal standing pressure and verify the valve lineup. Then, following the approved test plan, I secure the main pumps and capture the electric and diesel fire pump status. Next, I operate the jockey pump test path to a no-flow or shut-off condition where applicable. I record the stable pressure reading, read the pressure outlet and pressure indicator, and document the gauge behavior. The next step is confirming the jockey pump cut-in and cut-out sequence. The example values shown are 15.5 and 16.5 bar, but these must be verified or corrected against the approved criteria. The 23 bar shutoff head is an example, not a universal pass or fail limit. Final acceptance must follow the approved pump data and project requirements. After testing, I restore all pumps, confirm auto status, and review the trend for abnormal cycling. Repeated cycling may indicate leakage, incorrect settings, or an open drain. This slide defines a no-flow readiness check for the data center fire protection system, focused on churn pressure and the pump's response without intentional discharge. It proves several things at once: that the pump starts automatically, the controller logic works, the pump room is mechanically ready, pressure behaves as expected, and events are monitored and logged. During the test, I would record the pump mode and start time, discharge pressure, or P0, suction pressure, or P1, and the resulting net pressure using the approved gauge convention. I would also document any abnormal noise, vibration, leakage, or controller alarms. The gauge convention is especially important. Before testing, the team must define how net pressure will be calculated, because a suction instrument may show positive pressure or vacuum. That can change whether pressure is subtracted directly or corrected algebraically. Never mix conventions between test sheets. Finally, stopping must follow the approved procedure. Controllers should return to normal mode, PRV branches and distribution valves must be restored, and the complete result, including observations, should be logged. This section defines the core and diagnostic points for a pump performance flow test. The approved procedure establishes the required acceptance points, while additional readings may help diagnose behavior and define the curve more clearly. At churn or zero intentional flow, I record suction and discharge pressure, net pump pressure, speed, and mechanical condition. I also confirm automatic start, controller status, and the absence of abnormal relief discharge. At rated flow, I gradually adjust the common test loop to 100% of rated pump flow, then compare the measured pressure with the approved manufacturer curve and acceptance criteria. Where required, I also demonstrate the 150% overload flow point, checking driver load, suction conditions, and stable operation. Optional readings at 25, 50, 75, and 125% can improve the plotted curve, but they do not replace the required core points. Throughout the test, I record all relevant pressures, flow, speed, power or engine observations, controller mode, and relief behavior. I open the throttling valve slowly, stabilize readings, avoid water hammer, return water through the approved loop, and restore the system afterward. Pass or fail must follow the adopted requirements and approved equipment documentation, not a generic table. This slide provides the data sheet for an electric fire pump performance test within the data center fire protection system. The table is organized around 6 operating points, from 25% through 150% of the target flow. At each point, the test record should capture the actual flow rate, discharge and suction pressures, calculated net pressure, pump speed, and power input. These measurements allow the pump's performance to be documented consistently across its operating range. The test begins with the electric fire pump in automatic, test-ready mode. The jockey pump and diesel fire pump are controlled according to the approved procedure, and the pressure-reducing valve branches are closed as required for the performance test. For operation, the flow meter or test header valve is opened to approximately 30%, then adjusted slowly. The goal is to reach each target point in sequence, from 25% to 150%, while recording the corresponding readings in the table. The key requirement is controlled, steady adjustment at every test point, so the results are reliable and comparable. This slide provides a structured example data sheet for a diesel fire pump performance test. The table is organized around 6 flow targets, from 25% through 150%, with space to capture the measured flow rate, discharge and suction pressures, calculated net pressure, engine speed, and any relevant engine or power notes. The key purpose is to create a consistent record at every test point, so the pump's performance can be reviewed against the approved requirements. Before applying load, the diesel fire pump should be in automatic, test-ready mode. The electric fire pump and jockey pump are controlled according to the approved procedure, while fuel, cooling, batteries, and exhaust are checked in advance. During the test, flow should be increased gradually rather than changed abruptly. At each target, record the hydraulic readings together with diesel engine speed, temperature, vibration, exhaust condition, and fuel condition. This makes the sheet more than a pressure log. It documents both pump performance and engine operating condition, providing a clear basis for evaluating the test and identifying anything that needs follow-up. This section focuses on pressure measurement and the discipline required to calculate and document results correctly. PO refers to the discharge side pressure reading, while PI refers to the suction side reading. The gauge locations must be clearly identified on the schematic, and each gauge must have a suitable range and current calibration. Net pump pressure is not calculated by a universal rule. The approved method depends on the instruments installed and the gauge convention being used. When suction pressure is positive, test sheets commonly calculate net pressure as discharge pressure minus suction pressure. But if the suction gauge indicates vacuum, an algebraic correction is required. Data integrity is equally important. I need to use consistent units, record only stable readings, and photograph the gauges at each flow point whenever possible. I should also cross-check the flow meter reading against observations at the header discharge. Most importantly, I must not assume that PO plus PI or PO minus PI is correct. The approved project test form needs to define the calculation basis explicitly, so every result is repeatable and defensible. This section focuses on the pump test evidence pack and the acceptance record. The goal is not simply to perform the test, but to create a complete, traceable record showing what was tested, how it was tested, and whether the results are acceptable. The approved test method statement establishes the controls up front, including the valve lineup, flow path, permits, and required witnesses. The pump curve or test sheet provides the basis for comparing rated flow and pressure with actual performance. Controller screenshots and logs verify the key operating states: auto, start, run, and trouble. Calibration records for gauges and flow meters protect the credibility of the pressure and flow readings. The completed data table then captures the important test points, including shutoff, churn, and performance flow values. Photos or videos provide visual confirmation of valve positions, discharge, readings, and restoration. Finally, the restoration checklist confirms that the system was returned to normal, with pumps, valves, drains, and monitoring points all checked. A strong acceptance record connects every result to objective evidence. This section focuses on lifecycle readiness for the installed firewater system. The goal is to turn that system into a living maintenance program, rather than treating installation as the finish line. That program brings together 5 connected disciplines: inspect, test, maintain, restore, and document. Inspection and testing keep the pump room, firewater equipment, and brigade interfaces ready for use. Maintenance addresses conditions before they become failures, while recurring pressure or controller issues are tracked as trends, not isolated events. Restoration is equally important. Whenever equipment is tested, isolated, or impaired, the system must be returned to its normal operating condition in a controlled and verifiable way. The key principle is every activity closes with proof of restoration. That means confirming the normal valve lineup, returning controllers to auto, verifying stable pressure, clearing alarms, and recording signed evidence. In practice, documentation is not paperwork added at the end. It is the evidence that the system is ready, the work was completed correctly, and any remaining concern can be identified and managed. This pump room readiness view organizes the inspection into 7 practical checks, with each one tied to a specific piece of evidence. The key principle is to prove operation, not just confirm that equipment is present. First, start one pump using the approved method, then record pressure at the inlet and outlet, along with controller status, leakage, and vibration. Next, perform the main drain check by recording the change from static to residual pressure, while confirming safe drainage and complete closure. For the hydrant or fire department connection, verify access, serviceability, flow, and residual pressure evidence, and the brigade pre-plan. Then examine the pressure gauges for suitable range, zero position, readability, isolation, and calibration status. Valve supervision requires the normal position, lock or seal, identification, and tamper signal to be verified. For the diesel engine, check fuel, batteries, charger, cooling, exhaust, and controller alarms. Finally, confirm the jockey pump cuts in and out automatically, and investigate excessive cycling. After every test, restore the system deliberately. Close drains and test valves, return the valve lineup, place controllers in auto, verify pressure and alarms, inspect for leaks, and record and close the permit. This slide provides a practical IDM framework for maintaining a data center fire protection system over time. The key idea is that inspection, testing, and maintenance happen at different frequencies, and each activity should produce clear evidence. At the shift or daily level, the focus is awareness. Confirming the panel is normal, the pump room is accessible, there are no leaks or unplanned alarms, and pressure remains stable. Weekly checks go deeper, covering the pump room, controller, gauges, valve positions, and diesel fuel or battery condition. Monthly activities include operating the jockey and main pumps, testing supervisory signals, and exercising selected valves where applicable. Quarterly or semi-annual work adds hydrant and fire department connection checks, selected flow or drain tests, and alarm interface verification. Annually, the program includes pump performance and hydrant flow testing, tank inspection and cleaning as needed, and a full evidence review. Finally, after any change or event, the affected branch must be retested, drawings and valve lineups updated, and the impairment formally closed. Every activity needs documentation, from operator logs and checklists to functional records, event logs, and the annual IDM report. This slide provides a practical pump room readiness checklist, organized around 3 areas: water and hydraulic conditions, controls and power, and the diesel equipment and room itself. Readiness means every one of these conditions is normal, not merely that the pump starts. For the hydraulic side, I would verify the tank level, suction and discharge valves, pump seals, headers, relief and drain paths, and the test line position. I would also confirm that suction valves, anti-vortex intake paths, sensing lines, and the flow test loop are available and correctly aligned. Next, the electric fire pump, diesel fire pump, and jockey pump controllers should all be normal, with the correct automatic status and a healthy monitoring link. For the diesel system and room, I would check fuel quality and level, batteries and charger condition, ventilation, exhaust, drainage, access, and housekeeping. The key rule is simple. Hydraulic, electrical, diesel, controls, monitoring, access, and documentation must all be in an acceptable state. A single abnormal condition can turn an otherwise functional pump room into an impairment. This checklist focuses on 3 connected elements of fire department access: hydrants, the fire department connection, or FDC, and the brigade pre-plan. For hydrants, I'm looking for more than simply confirming their location. They need to be accessible and visible, with serviceable caps, threads, and operating nuts. I also need to verify there is no leakage or physical damage, and that flow and residual pressure testing is completed when required. Markers and numbering should remain clear and maintained. For the FDC, the working area must be clear, caps and chains must be intact, and signage must identify the system being served. The check valve and drain conditions should be known, with no obstruction from vehicles, fencing, or landscaping. The brigade pre-plan completes the picture. Access roads and staging areas must be available, security procedures tested, and the pump room and riser route familiar to responders. The latest site plan should be shared with the response team. Most importantly, readiness must be verified by physically walking the site. Drawings alone cannot confirm the real access path during an emergency. This section focuses on tank inspection, water quality, and the controls required when one tank cell is taken out of service. During inspection, I want to verify that anti-vortex plates, suction bells, and every pump intake are unobstructed. We also check level indication and alarms, access and safety provisions, interior corrosion or sediment, overflow, drain and refill functions, and any signs of leakage or foundation damage. Water quality is equally important. Sediment, corrosion, biological growth, and contamination can restrict strainers or pump suction paths. That is why flushing and cleaning records matter, as does confirming the quality of the refill source. For a one-cell outage, we must confirm the remaining usable volume and make sure the pump suction path is still available. If the required arrangement cannot be demonstrated, an impairment permit is needed, with notification to the authority having jurisdiction or the insurer where required. After cleaning, retest the system and formally restore it. Tank cleaning is a controlled fire protection impairment, not routine housekeeping, because it can change the risk posture of the entire campus. This section focuses on failure modes and the safeguards that prevent them from becoming serious protection system deficiencies. The key idea is that many failures are not dramatic equipment breakdowns. They are configuration, maintenance, or restoration problems that can quietly reduce system performance. A closed suction or discharge valve can prevent the pump from meeting demand, so valves need supervision, clear valve charts, and a locked-open normal position. Low tank level creates both reduced water duration and suction risk. That calls for level alarms, a refill plan, inspection, testing, and maintenance, or ITM, along with an impairment procedure. Frequent jockey pump cycling can indicate leakage or pressure instability, so trend starts and inspect leaks, check valves, and drains. Diesel pump reliability depends on battery and charger testing, alarms, and periodic start tests. The fire department connection, or FDC, must remain accessible and unobstructed, with walkdowns, signage, and access control. Finally, pressure-reducing valves require specialist adjustment, documented settings, and retesting. After any test, use a restoration checklist and witnessed closeout to ensure the test valve is actually closed. Restoration discipline is the safeguard that prevents a completed test from leaving the system impaired. This slide defines the impairment control and restoration workflow for the fire protection system. The process moves through 7 controlled steps: request, assess, approve, protect, execute, restore, and close. That sequence ensures an impairment is not treated as an informal maintenance task, but as a managed operational risk. Typical triggers include an unavailable fire pump, an isolated tank cell or hydrant loop, an unavailable fire department connection, a controller in OFF or trouble, or a critical valve that has been closed. Once identified, compensatory measures must be assigned. These may include a fire watch or patrol, a temporary water supply or tanker plan, limits on high-risk work, required notification to the authority having jurisdiction or insurer, and accelerated repair and retesting. Restoration is not complete until there is proof. Valves are back to their normal lineup, pump controllers are in auto, pressure is normal, monitoring is clear, and the retest is finished. The permit must then be closed and records filed. No temporary bypass or abnormal valve position should survive a shift handover without formal documentation, an affected zone map, and owner approval. This slide shifts the focus from system architecture to the people who keep that architecture trustworthy throughout its life cycle. The PNID provides the map, source and tank, suction and discharge paths, test returns, pressure sensing, relief or waste routes, and the pressure lines that support impairment warnings. But a map is only useful when the evidence behind it is current and verified. For the source or tank, that means confirming usable volume and reviewing anti-vortex inspection records. The electric main requires proof of automatic starting and CRV drainage. The diesel standby adds independent start logs, fuel condition, and visible waste cone evidence. Finally, common systems depend on calibrated flow meters and verified valve lineups. The critical point is that unauthorized changes can defeat the defense immediately. Manipulating controller logic or turning a closed valve without formal management of change approval removes confidence in the protection. The unbroken chain, therefore, depends on sound physics at commissioning, followed by disciplined human verification every day. This slide is an operator response playbook for 3 common conditions: a pump run alarm, a supervisory or trouble signal, and system reset or restoration. For a pump run alarm, the priority is to acknowledge the alarm without stopping the pump prematurely. I need to identify which pump is running and why, dispatch a field team to the pump room, confirm the protected system remains properly supported, and record the time, PO, PI, and controller status. For supervisory or trouble conditions, I identify the affected pump, valve, or branch, then determine whether fire protection is impaired. The responsible discipline must be notified, and fire watch or other impairment controls applied when necessary. Corrections should be tracked through retest. Reset and restoration begin with a physical inspection, not simply clearing the alarm. Controllers return to auto, valves and drains are verified normal, and BMS, FACP, and SOC status are confirmed. The event report, and MOC when required, must then be closed. The critical habit is to ask what changed, what is affected, who owns the field response, and what evidence proves normal operation is restored. This workshop is about building a practical firewater readiness register, one that turns system knowledge into a clear, repeatable record. The goal is to connect each protected service with the information needed to verify its readiness. Start by identifying what the service protects, such as sprinkler zones, hydrants, standpipes, or an FDC branch. Then document its normal water source and the expected response of the jockey, electric, and diesel fire pumps, including their start settings and controller status. The register should also make valve control unambiguous. Record each key valve's normal position, how it is supervised or locked, and who is authorized to operate it. For testing, specify the method, whether that is a shutoff, churn, performance, main drain, hydrant flow, or FDC condition check. Finally, assign an evidence owner, so responsibility does not disappear between contractors, facility staff, commissioning, and security operations. The most important field is restoration proof. Confirm pumps are in auto, valves are normal, drains are closed, logs are captured, and any permit is formally closed. This knowledge check brings together the main operational decisions from Module 08. As you work through it, focus not only on what each component does, but on how the components interact during testing and emergencies. For question 1, consider why jockey pump cut-in and cut-out pressures must be coordinated with the main fire pump start settings. The goal is to avoid unwanted starts while still maintaining system readiness. Question 2 asks what documentation and safety evidence demonstrate that a shutoff head test was completed correctly. Questions 3 and 4 move into system configuration and control. Be prepared to explain why fire department connections and tank refill connections serve different functions, and what could happen if a pressure-reducing valve is misset or left out of its normal position. Finally, consider how the test header or flow meter supports pump testing across the required range, from 25 to 150%, and identify the conditions that would require a formal impairment permit during maintenance. The key theme is controlled, documented, and safe operation. This section focuses on a disciplined path from water system calculations to field-proven decisions. The goal is not to preserve every equation from the source material. Instead, 28 focused checks replace the 142 slide source appendix, and each check is included because it can change demand, storage, pump, pressure control, or acceptance decisions. The calculation chain is deliberately linear. We begin by establishing the basis, then quantify demand, evaluate hydraulics, define the system architecture, select equipment, and finally confirm performance through acceptance testing. In practice, that means moving from inputs to an equation, to substituted values, to a result, and then to the decision that result supports. Every term, unit, and value source should be explained in the notes, so the work can be reviewed and reproduced. It is also important to keep the boundary clear. Screens and calculations do not replace certified manufacturer data or hydraulic data. They support selection, but the final decision must connect directly to witnessed field tests. The overall sequence is simple: calculate, select, verify, and commission. This slide establishes the control discipline for calculations in the fire protection system. The central rule is simple: carry the units, pressure datum, and source ownership on every line. That means distinguishing flow from volume and documenting whether pressure is gauge, absolute, or net pump pressure. For flow and volume, 1 US gallon per minute equals 0.06309 liters per second. 1 US gallon equals 3.78541 liters, and 1 cubic meter equals 264.172 US gallons. When demand changes over time, the total volume must come from integrating the flow rate, Q of T. For pressure and head, 1 psi equals 6.8948 kilopascals, while 1 meter of water equals 1.422 psi. The source of every input also matters. Tag values as code or AHJ requirements, project data, measured results, OEM information, or owner assumptions. Certified equipment curves and field data take priority over training examples. Finally, freeze the scenario, show equations with units, use unrounded values, select equipment from its complete listed envelope, and connect the calculation to a field acceptance test. This slide shows how the calculation register controls the basis of design. The central principle is every input has one owner and one evidence source. That makes the calculation traceable, and it also makes changes easier to manage. The register groups inputs into 6 families. Code minimums, such as the OH2 density and area, are owned by the fire engineer and supported by a clause extract. AHJ or Damker requirements, including the 1,500 gallon per minute flow for 120 minutes, are confirmed through the approval letter. Geometry relies on surveyed information, BAM, and survey records. OEM inputs, such as pump curves and valve losses, come from certified supplier data. Owner resilience decisions, like using 2 tank cells, are tied to the design basis. Finally, measured values, such as static and residual pressure, are supported by commissioning test records. Each row also identifies the trigger for an update, from a code or fire flow revision to a retest or impairment. The design note is important. Assumptions stay visible until approved evidence replaces them, and no unexplained safety factor is hidden in the result. The governing references are NFPA 3, NFPA 4, and the project's design basis and change control procedure. This slide establishes how fire protection water demand is governed across different services. The key principle is that each system is calculated from its own hydraulic basis, duration, concurrency rules, and governing authority. For example, the pre-action sprinkler demand is 577 gallons per minute for 60 minutes, while standpipe demand is 1,000 gallons per minute for 30 minutes. Campus hydrants use a separate external fire flow input of 1,500 gallons per minute for 120 minutes, and special systems, such as foam and water mist, follow their listed design basis. The demand matrix prevents unrelated maximums from being added twice. Instead of simply summing every peak value, we identify which systems operate together and which are dedicated, supplemental, or governed by the adopted code and authority having jurisdiction. For the work tank case, the integrated demand is 1,800 gallons per minute for 60 minutes, followed by 1,500 gallons per minute for another 60 minutes. That sequence reflects the governing scenario without treating every special system maximum as simultaneous. The final design must remain aligned with NFPA, SNI-FM guidance, the approved hazard schedule, the hydraulic model, and HJ requirements. This slide converts the time-phase demand profile into a usable water storage requirement. The formula sums each stage flow multiplied by its duration, then applies the conversion factor from US gallons to cubic meters. The key result is 749. 5 cubic meters of usable water. During the first hour, the combined demand is 1,800 US gallons per minute for 60 minutes. That produces 408.8 cubic meters, representing yard flow together with the 300 gallon per minute sprinkler overlay. During the second hour, demand drops to 1,500 gallons per minute for another 60 minutes, producing 340.7 cubic meters as yard flow continues after the sprinkler period. Adding those two stages gives 749.5 cubic meters, or approximately 198,000 US gallons, that can actually be drawn while meeting the approved scenario. The gross tank selection is higher because 6.31% is treated as unusable reserve. Dividing by the usable fraction gives a required gross capacity of about 800 cubic meters, leaving 50.5 cubic meters unavailable for drawdown. The engineering decision is therefore to select an 800 cubic meter gross tank, subject to AHJ concurrence on concurrency, duration, and any verified refill credit. This slide defines the design input for the Module 08 fire protection system. The key value is the approved 577 gallons per minute pump flow basis, which is carried forward from the Module 07 hydraulic model. The table shows how that value is established. The remote area calculation includes 3 branches, with flows of 106, 108, and 113 gallons per minute. Together, they produce an approved remote area hydraulic result of 327 gallons per minute. A 250 gallon per minute hose allowance is then added at the approved point, producing the 577 gallon per minute system total. The branch data also records sprinkler count, elevation, cross-main loss, and node pressure. Those details document the hydraulic conditions behind the approved result, rather than representing separate pump selections. The pump flow basis is taken before the riser and header, and the instruction is to select the next listed pump rating above this requirement. The governing basis is the approved Module 07 model, together with NFPA 13, SNI 3989, and NFPA 20 pump selection requirements. This creates a clear interface between the sprinkler demand calculation and the pump selection step. This slide shows the sprinkler pump duty calculation for the data center fire protection system. The key question is how much net pressure the pump must add at the design flow. The calculation combines 4 terms: the required residual pressure at the most remote sprinkler, elevation pressure, route losses through piping and devices, and any available suction pressure. Here, the remote sprinkler requires 21.6 psi. The 70-foot elevation difference contributes 99.5 psi, using the stated conversion factor, and the calculated pipe and device losses add another 18.8 psi. With no suction pressure deduction shown in this summary, the required duty is 21.6 plus 99.5 plus 18.8, or 139.9 psi, at a system demand of 577 gallons per minute. The engineering decision is to select a listed 750 GPM pump that can provide at least 140 psi at this operating point. The certified pump curve must also remain acceptable at churn and at 150% flow. This selection is governed by the cited NFPA, SNI, FM, hazard schedule, hydraulic model, and certified equipment requirements. This slide works through the standpipe flow calculation for a fully sprinklered building with 4 protected stairs, and the key point is that the final demand depends on the adopted rule and its conditions. The formula starts with 500 gallons per minute, then adds 250 for each additional hydraulically remote riser, up to the applicable limit. With n equal to 4, the uncapped calculation is 500 plus 250 times 3, which produces 1,250 gallons per minute. For this worked example, the fully sprinklered building limit is confirmed, so we use the smaller of 1,250 and 1,000. The governing simultaneous standpipe flow is therefore 1,000 gallons per minute, or 63.09 liters per second. Over a 30-minute duration, that flow represents approximately 113.6 cubic meters of water. The engineering decision is important. Apply the 1000 GPM cap only when the adopted addition conditions are satisfied and accepted by the authority having jurisdiction. Otherwise, retain the uncapped 1250 GPM result. The governing references are NFPA 14, the adopted Building and Fire Code, and AHJ or DAMCR approval. This calculation establishes the standpipe total dynamic head, or TDH, required at the pump. The governing point is the highest required valve, where the system must maintain a remote residual pressure of 100 psi. Next, we account for elevation. The 70-meter vertical lift is converted using 1.422 psi per meter, producing 99.5 psi from the pump datum to the outlet. Route losses through the pipe and devices add another 25 psi, made up of the listed component losses: 3.2, 1.6, 5.4, and 14.8 psi. Adding these requirements gives 224.5 psi. 100 psi for the remote residual, 99.5 psi for elevation, and 25 psi for friction and device losses. No suction pressure is subtracted in this displayed duty, so the selection is rounded to 225 psi nominal. The engineering decision is to select a listed 1,500 GPM pump at 225 psi for the separated hydrant and standpipe set. Final duty still depends on the approved suction pressure and the certified pump curve, with verification against the listed NFPA, SNI, FM, code, and AHJ requirements. This slide shows how to determine the maximum static pressure a lower floor fire protection zone may experience when the pump is running at churn or zero flow. The key relationship is straightforward. Maximum system pressure equals the highest credible suction pressure, plus the pump's certified net churn pressure. The certified pump curve, not simply the rated pressure, governs the calculation. In this worked example, the pump is rated at 225 psi, and the certified churn pressure is shown as 270 psi, or 120% of rated. We then add 5 psi for the maximum suction condition, such as a high tank level or elevated supply pressure. That produces a maximum total of 275 psi at the lower floor components. This value is the pressure that must be used to screen the header and upstream equipment. Any downstream hose valves or other components that cannot accept it may require pressure-reducing valves or a separate pressure zone. The design should be checked against the certified pump, driver, and controller data, along with the applicable NFPA, FM, SNI, building code, and authority having jurisdiction requirements. This calculation checks the private main ring under 2 operating conditions: normal flow, with supply available in both directions, and a credible single isolation condition, where one section is closed. The governing case is the lowest residual pressure at any remote node across the approved isolation states. The hydraulic relationship is straightforward, but every term matters. Pressure at a node starts with source pressure from the tank and pump header, then decreases because of elevation, friction along the selected route, and losses through devices. The alternate route must still deliver the full design flow when a section is isolated, rather than relying on the convenience of having every valve open. That is why the engineering decision is to size the campus ring around the remote hydrant requirement during the defined credible isolation. Here, the critical point is identified as hydrant H07. Acceptance is then demonstrated through the required flow and residual pressure proof, using pitot measurements and residual readings. The governing references are NFPA 24, 2025 edition, Chapter 11, FM Data Sheet 3-10, the approved private main pipe schedule, and the water flow test. This slide works through a velocity check for the yard main. The example considers a DN 300 pipe carrying 2,000 gallons per minute, with an inside diameter of 0.303 meters. We begin by converting the flow to metric units. 2,000 gallons per minute becomes approximately 0.1262 cubic meters per second. Next, we calculate the internal flow area using pi times the diameter squared, divided by 4. With the approved pipe dimension, that area is 0.0721 square meters. Finally, we divide flow by area. The result is 1.75 meters per second, which is the average water velocity through the pipe. The important engineering point is that this velocity is a screening metric, not the final basis for selecting the pipe diameter. The final decision must also consider remote residual pressure, surge, available water supply, and credible isolation hydraulics. The governing checks reference NFPA 24, Chapter 11, FM Data Sheet 3-10, the approved private main pipe schedule, and the water flow test. So, this calculation is a useful verification screen, but not a substitute for the complete hydraulic assessment. This slide shows how we determine the pressure available at the remote hydrant, using the worked isolation case. The governing relationship is straightforward. Remote pressure equals source flowing pressure, minus elevation loss, route and device losses, and hydrant internal loss. The source is flowing at 55 psi. Elevation contributes 4.3 psi of loss, based on a 3-meter rise. Route and branch losses add to 11.0 psi, combining 6.2 and 4.8 psi. Finally, the hydrant internal loss is 3.0 psi. Subtracting those values gives a hydrant residual pressure of 36.7 psi. That is comfortably above the required 20 psi after route and hydrant losses at 1,500 gallons per minute. The resulting hydraulic margin is 16.7 psi. This is an engineering check, not the final approval by itself. We still need to verify the result against the final pump curve, the actual static water level, and a field flow test. The governing references are NFPA 24, 2025 Chapter 11, FMDS 3-10, and the approved private main pipe schedule and water flow test. This calculation determines the fire engine discharge pressure needed to support the roof standpipe. The governing formula adds 4 components: the required residual pressure at the remote outlet, elevation pressure, building and FDC losses, and the hose or FDC allowance. At the highest hose valve, the required remote residual is 100 psi. The roof outlet is 70 feet above grade, and using 1.422 psi per foot produces approximately 99.5 psi of elevation pressure. Building and FDC losses contribute another 33 psi, including pipe, devices, the inlet path, and the building route. Finally, the calculation includes a 5.5 psi hose allowance. Adding those values gives 100 plus 99.5 plus 33 plus 5.5 for approximately 238 psi at the engine discharge. This is an engineering decision, not just a theoretical result. Before finalizing the FDC strategy, I need to confirm the damper apparatus and hose pressure capability, the number and size of inlets, check valve arrangement, signage, and connection access. The design should also be checked against NFPA 14, the adopted fire code, and the applicable private main and water flow requirements. This slide calculates the tank volume that cannot be counted on for fire protection demand. The gross tank volume is 800 cubic meters, arranged as two 400 cubic meter cells. After accounting for the governing integrated scenario, the verified usable volume is 749.5 cubic meters. The difference is the unusable reserve, 800 minus 749.5, which equals 50.5 cubic meters, or 25.25 cubic meters per cell. Expressed as a fraction of the total tank, that reserve is 50.5 divided by 800, or 6.31%. The key engineering point is that this is not simply a generic percentage allowance. The reserve has to be reconciled with the actual low-level shutdown point, intake submergence requirements, floor slope, sediment, and measurement uncertainty. In other words, the calculated volume must agree with the tank's physical level geometry and approved operating levels. The governing references shown here include NFPA 22 from 2023, NFPA 20 from 2025, FM Data Sheet 3 to 29, and the approved tank and intake arrangement. This slide calculates the net positive suction head available, or NPSH, for the fire pump under the governing minimum level condition. The formula is atmospheric head plus static head, minus vapor pressure head and suction side losses. Each term is expressed in meters of water. For this worked site, the atmospheric head is 10.33 meters, based on near sea level conditions. The minimum water level contributes 1.30 meters of static head. At the assumed water temperature of 30 degrees Celsius, the vapor head is 0.44 meters. Finally, the verified total suction loss is 0.20 meters. Substituting those values gives 10.33 plus 1.30, minus 0.44, minus 0.20, for 99 meters of NPSH available. That result is not the final pump acceptance decision by itself. I need to compare 10.99 meters with the certified pump's NPSH required at both rated flow and 150% flow, while preserving the owner or OEM margin. Before final confirmation, the site altitude and maximum water temperature also need to be verified. The governing references include NFPA 20, SNI 6570, FM Data Sheet 3 to 7, and the certified pump, driver, controller, and OEM curve data. This slide checks the pump's net positive suction head margin at the governing flow. The calculation is straightforward. NPSH margin equals NPSH available, or NPSH, minus the certified NPSH required, or NPSCHAR. Using the minimum tank level, NPSH is 10.99 meters. The selected pump and impeller require 6.50 meters at the governing flow. Subtracting those values gives an absolute margin of 4.49 meters, which is positive. The ratio is 1.69, but that figure is provided for screening only. The OEM certified criterion for the selected pump governs the final decision. From an engineering standpoint, we retain this margin to allow for fouling, uncertainty in tank level, and flow beyond the rated condition. It is also important not to treat NPSCHAR as a design target. It must come from the certified selected pump curve. Finally, a positive NPSH margin does not replace compliance with suction piping requirements. The governing references include NFPA 20:2025, SNI 6570:2023, FM Data Sheet 3 to 7, and the certified pump, driver, and controller data. This slide separates three civil water route checks that are often confused: gravity overflow, controlled maintenance drainage, and fire water runoff. The distinction matters because each route has a different purpose and design basis. For overflow, the maximum credible refill inflow is 30 liters per second. Applying the 1.25 margin gives a required gravity capacity of 37.5 liters per second, providing hydraulic proof with a 25% allowance. This route must remain gravity capable even if normal power is lost. For a one-cell maintenance drain, the calculation is 400 cubic meters divided by 8 hours, resulting in approximately 13.9 liters per second. That is a controlled discharge route, not an emergency overflow path. The fire water runoff calculation estimates 119.2 cubic meters from the stated fire flow, duration, and capture fraction, so the selected containment volume is 140 cubic meters. The key engineering decision is to keep these three systems physically and functionally separate, based on NFPA 22, verified refill and cell data, and the approved drainage, containment, and environmental plan. This slide calculates the pump pressure required for the hydrant and combined routes, using the remote roof hose valve as the governing outlet. The calculation starts with the required residual pressure at that outlet, which is 100 psi. We then add the elevation pressure from the pump datum to the 70-meter outlet, 70 multiplied by 1.422, or 99.5 psi. Finally, we include 25 psi for pipe and device losses along the governing route and subtract available suction pressure. In this case, suction is taken as 0, so the total is 100 plus 99.5 plus 25, giving 224.5 psi net pump pressure. The engineering decision is to select a 225 psi nominal net duty. That duty applies specifically to the hydrant and combined route. The separated sprinkler train is not replaced by this value. It retains its own 140 psi work duty and certified pump curve. The reference basis is NFPA 14 for remote pressure and elevation, together with NFPA 20 for rated point and certified curve verification. This slide explains how the selected fire pump is evaluated across its complete performance curve, rather than at only one rated point. The key idea is that acceptance depends on satisfying every listed condition: churn, operating flow, rated flow, and 150% flow. At churn or zero flow, the system must remain within its pressure rating, with no unacceptable overpressure. At the operating point, the pump must meet the required route pressure at 1,800 gallons per minute and intersect the system curve. The rated point confirms the nominal 2,000 gallon per minute duty at 225 psi, while the 150% point checks the pump at 3,000 gallons per minute against the listed minimum pressure and maximum brake power. The review also includes NPSH at all points, ensuring adequate margin to prevent cavitation, along with confirmation that the motor or engine can provide the required power. The final decision is based on the complete certified curve, the selected impeller, the driver, and the controller, not one isolated number. This evaluation follows the governing references listed here, including NFPA 20, SNI 6570, and FMDS 3-7. This slide calculates the pump shaft input at the rated operating point, then explains why that number alone does not determine the final driver selection. The rated flow is 2,000 gallons per minute, converted to 0.1262 cubic meters per second. The corresponding head is 225 psi, or 158.2 meters of water head. Using water density, gravity, flow, and head, the calculated hydraulic power is 195.9 kilowatts. To account for pump efficiency, the hydraulic power is divided by the stated efficiency of 0.78. That produces a rated point shaft input of approximately 251 kilowatts. The important qualification is that this is a preliminary estimate at one operating point, not necessarily the highest power the pump can demand across its certified curve. The final driver must follow the maximum certified brake power, not just the rated point calculation. Therefore, the 300 kilowatt motor should be selected only when the certified maximum brake power curve, along with the listed motor and controller ratings, confirms that choice. The governing references include NFPA 20, SNI 6570, FMDS 3-7, and the certified equipment data. This slide shows how we select the diesel engine for the fire pump after accounting for site conditions. The key requirement is that power available at the site, calculated from the certified nameplate rating and the OEM temperature and altitude derating factors, must be at least equal to the pump's maximum brake power. The engine must cover the full certified pump power curve, not just a single operating point. In this worked example, the maximum brake power is 270 kilowatts. The temperature factor is 0.96, based on the OEM design ambient, and the altitude factor is 0.99 for the worked Jakarta site. So, the required nameplate rating is calculated as 270 divided by 0.96 times 0.99, which gives approximately 284 kilowatts. Because the engine must use the next approved rating, the selection becomes 300 kilowatts. That rating also needs to be provided as a complete, matched package, including cooling, exhaust, fuel, and controller components. The final decision is therefore based on certified pump, driver, and controller data, together with the applicable NFPA, SNI, and FM references. This slide shows the diesel fuel tank calculation using a known, certified consumption rate. The engine consumes 75 liters per hour at the required load, and the adopted operating duration is 12 hours. That gives us a basic operating volume of 900 liters. We then apply the listed tank allowances, 5% for fuel expansion and 5% for the sump, for a combined allowance of 10%. Using the formula, preliminary tank volume equals consumption multiplied by duration, multiplied by 1 plus the expansion and sump allowances. In this case, 900 liters times 1.10 produces a required tank volume of 990 liters. The practical engineering decision is to select a tank of at least 1,000 liters on this route, while verifying the adopted project duration. Where available, the certified engine fuel consumption curve should govern the calculation. We also need to reconcile usable fuel, expansion space, sump capacity, return fuel, and the day tank arrangement. The governing references include NFPA 20:2025, certified engine data, and applicable environmental and fuel requirements. This slide shows the calculation used to verify ventilation and exhaust performance for the diesel room. The ventilation requirement is governed by the greater of two values: the OEM minimum airflow, or the airflow needed to remove the heat released into the room. The selected engine and radiator package rejects 120 kilowatts of heat, and the approved room temperature rise is 10 kelvins. Using the stated air properties, the heat balance calculation is 120 divided by 1.2 times 1.005 times 10, which gives approximately 9.95 cubic meters per second. That value is rounded up, so the design must provide at least 10 cubic meters per second, while still being checked against the OEM airflow requirement. The exhaust check is separate. The silencer, piping, and fittings contribute 4.0, 2.2, and 1.3 kilopascals, for a total back pressure of 7.5 kilopascals. This is below the 10 kilopascal OEM limit. The engineering decision is a pass only when both conditions are satisfied, including verification of recirculation and louvre or filter losses, using the listed standards and manufacturer limits. This slide works through the jockey-pump duty calculation. The first decision is flow. The pump must exceed credible normal leakage, so we compare 6 gallons per minute of leakage with the 15 gallon per minute screening value. The selected jockey flow is 15 GPM, or 0.000946 cubic meters per second. It receives no credit toward fire flow. Next, we determine the required head from the discharge pressure. Dividing 235 psi by 1.422 gives approximately 165.3 meters, which is above normal system pressure. That head, combined with the selected flow, water density, gravity, and a worked efficiency of 70%, produces a shaft input of about 2.19 kilowatts, rounded to 2.2 kilowatts. The motor and package should therefore use the next practical listed rating, shown here as 3 to 4 kilowatts, but the final choice must be checked against the actual certified pump curve. We also need to verify stable cut-in and cut-out behavior. The governing principle is that credible leakage, not fire demand, sets jockey pump flow, consistent with the listed NFPA, SNI, FM, and certified equipment references. This slide shows the pressure ladder for a high-rise fire protection system. The key calculation is that static pressure decreases by approximately 9.95 psi for every 7 meters of elevation gain. Starting with a 225 psi rated condition in the pump room, the predicted residual pressure declines to 187 psi at level 3, 163 psi at level 5, 126 psi at level 8, and about 100.5 psi at the roof. The design challenge is balancing adequate pressure at the highest remote point with overpressure protection on the lower floors. The table also includes allowances for flow loss, which increase with elevation and system reach. That is why pressure control may require pressure-reducing valves, zone review, or direct control, depending on the level. We also need to evaluate both rated flow and churn conditions. Lower floor overpressure commonly appears during churn or very low flow, when friction losses are minimal, so certified churn data is essential. Final decisions should be checked against NFPA 14, NFPA 20, SNI 6570, FM guidance, adopted fire code, and applicable AHJ requirements. This calculation shows how to establish the high flow setting for a low zone pressure reducing valve, or PRV. The zone hydraulic model provides an inlet pressure of 210 psi, while the downstream design target is 150 psi under flowing conditions. The governing relationship is straightforward. Pressure reduction across the valve equals inlet pressure minus outlet pressure. So, 210 minus 150 gives a required reduction of 60 psi at the specified flow. That number is not, by itself, enough to select the valve. I also need to verify the manufacturer's listed high flow curve at the required flow, using the correct valve size and configuration. The selection must remain stable and serviceable, while staying within the valve's differential pressure limits. I should also check for potential cavitation and excessive noise, since both can affect reliability and maintenance. The engineering decision, then, is to select the listed PRV based on the OEM high flow data, and confirm that it satisfies the system's hydraulic requirements and applicable governing references, including NFPA 14, the adopted fire code, and AHJ or Brigade Interface requirements. This slide screens the potential water hammer pressure rise caused by an instantaneous closure. The governing relationship is delta P equals rho times A times delta V. Pressure rise depends on water density, wave speed, and the rapid change in flow velocity. Using the worked values shown here, water density is 1,000 kilograms per cubic meter, wave speed is 1,000 meters per second, and the velocity change is 1.75 meters per second, based on the DN 300 rated flow screen. Multiplying those terms gives 1.75 megapascals, or 5 bar of pressure rise. This is an instantaneous upper screen value, not a substitute for a project-specific transient model. The engineering decision is to perform a transient analysis when fast valves, check valve slam, long mains, or pump trips can create a rapid velocity change. From there, control closure time and provide surge mitigation as required. The final assessment should use the governing references, approved pipe schedules, water flow testing, and the actual valve, pipe, and mechanical data. This slide presents the final controlled equipment schedule, bringing the preferred separated design together with the conditional combined alternate. The baseline is clear. Sprinkler and hydrant or standpipe systems remain separate, with independent headers, controllers, and test loops. That separation is the governing design selection. For firewater storage, the schedule provides 800 cubic meters gross, arranged as two 400 cubic meter cells, while recognizing that this is a shared source rather than a fully 2N arrangement. The sprinkler train is selected at 750 gallons per minute, and the hydrant and standpipe train at 1,500 gallons per minute and 225 psi. Both require performance testing, including remote node or roof residual verification and pump curve confirmation. The combined alternate increases capacity to 2,000 gallons per minute, but it also creates a larger common cause boundary, so it remains conditional on the demand matrix, hydraulic curve, and an owner or AHJ decision. Jockey pumps receive no fire flow credit, and pressure control requires high-pressure equipment, listed PRVs, zoning, and surge review. Final acceptance follows the applicable NFPA standards and certified equipment data. This reference slide brings together the abbreviations used throughout the water system and fire pump calculations. The first group covers the core hydraulic variables. Q is flow, H is head, and TDH is total dynamic head. When using Hayes and Williams, remember that the roughness coefficient, pipe length, actual inside diameter, and flow all affect friction loss. A key distinction is between sprinkler K, which describes sprinkler discharge, and the fitting loss coefficients, shown as sigma K. They are not interchangeable. NPSH available and required must also be compared at the same flow, datum, and temperature. The pump and valve abbreviations identify equipment roles. EFP and DFP refer to electric and diesel fire pumps, while the jockey pump manages leakage. PRVs, main relief valves, and casing relief valves support pressure zoning and zero flow protection. FDC, AHJ, and DAMCR describe the fire department interface and approval process. Finally, PO, PI, and RPM support test records, while OEM, commissioning, and IDM establish lifecycle responsibility. OEM selection governs the driver and battery data, including BHP, CCA, and ampere hours. This slide gathers the primary references that support the fire protection system design, and it makes an important distinction between published standards and project-specific evidence. The legally adopted edition, Local Indonesian Regulation and SNI Requirements, AHJ or DAMCR interpretation, listed equipment data, and the approved project design basis must govern the final decision. For water storage and mains, the references cover sprinkler demand, standpipes and fire department connections, pumps and controllers, tanks, private fire service mains, and inspection, testing, and maintenance. The listed SNI standards provide the applicable Indonesian framework alongside the NFPA documents. The commissioning and local requirements add another layer. NFPA 3 addresses the commissioning program, while NFPA 4 addresses integrated system testing. These must be coordinated with adopted building and fire codes, fire flow decisions, owner resilience and impairment policies, and formal change control. Finally, the design should be supported by FM guidance and project evidence, including hazard schedules, surveyed levels, hydraulic models, certified equipment curves, tank and drainage information, and complete as-built, acceptance, and restoration records. Together, these references create a traceable basis for design, approval, testing, and future maintenance. This slide establishes how evidence is controlled for the Data Center Fire Protection System, Module 08. The calculation pack is issued with a controlled evidence register, so every important design and commissioning input has an owner, an approval path, an update trigger, and a defined final record. The register covers 6 evidence packages. The design basis captures demand, concurrency, and duration assumptions. Hydraulic models document nodes, routes, and supply curves. Certified manufacturer data supports the pumps, drivers, controllers, pressure-reducing valves, and fire department connections. Field tests provide proof through Churn, 100 and 150% flow testing, and Hydrant or FDC testing. As-built records confirm actual levels, routes, valve positions, and settings, while operations documentation controls inspection, testing, maintenance, impairment, and restoration procedures. The central rule is approved evidence and field proof must agree before a calculation becomes an as-built record. Any training input must be replaced through formal change control. This process is governed by NFPA 3 and 4, NFPA 25, and the project's document control, commissioning, and handover requirements. This final review closes the complete Module 08 chain, from approved demand through witnessed remote proof. The key question is whether every calculation and record describes the same approved and installed fire protection system. The review begins with demand, scenario, concurrency, and peak duration linked across the sprinkler, standpipe, and yard systems. Storage then converts the required flow over time into usable volume, gross volume, reserve, drawdown, and refill evidence. Suction confirms that losses, tank conditions, temperature, altitude, and minimum water level still provide adequate NPSH margin. The pump and driver must connect duty, performance curve, power, and fuel to certified testing. Distribution and the FDC complete the hydraulic path through ring configuration, isolation, residual pressure, and flow testing. The final discipline is acceptance and IDM, including settings, testing, restoration, commissioning, and operations evidence. Closure means these interfaces are consistent, certified as built, approved, and witnessed. The primary references include NFPA, FM, SNI, and AHJ requirements. Most rows remain marked Verify, while acceptance and IDM is marked Close, so the remaining task is disciplined evidence confirmation, not another redesign. This module closes the chain for data center fire water systems, from approved demand and usable water through pump and driver selection, brigade interface, and lifecycle evidence. The key transition now is from training inputs to approved project-specific evidence. Before design review, every affected interface must be recalculated whenever the design changes. Finally, the completed system needs to be proven through witness testing, followed by disciplined restoration. With those closeout checks complete, the work is ready for project-specific review and progression to Module 09.